The expansion of space creates a situation where we can observe only a tiny fraction of cosmic history in any given region. We see distant galaxies as they were billions of years ago. We cannot observe what they look like now. We see our local neighborhood as it currently is. We cannot see what it looked like billions of years ago from our current vantage point, though we can infer this from observations of similar distant systems. This limitation shapes how we study cosmic evolution. The standard candles in astronomy, objects with known luminosity, provide crucial distance measurements or reach similar peak brightness because they result from white dwarfs reaching a critical mass. Cepheid variables have periods related to their luminosity. By comparing apparent brightness to known luminosity, astronomers calculate distances using the inverse square law. These measurements form rungs on the cosmic distance ladder, each building on previous ones. The standard rulers in cosmology work similarly, but use known physical sizes instead of luminosities. The sound horizon at recombination has a calculable size based on early universe physics. This size appears in both the cosmic microwave background pattern and later matter distribution as baryon acoustic oscillations. Measuring the apparent angular size of this standard ruler at different redshifts reveals the expansion history. The Tully-Fisher relation connects galaxy rotation speeds to their luminosities, providing another distance indicator. Faster rotating galaxies are more luminous. By measuring rotation speeds and apparent brightness, astronomers estimate distances. This technique works for spiral galaxies and extends the distance ladder beyond the range where individual stars can be resolved. The fundamental plane relation for elliptical galaxies serves a similar purpose, relating their sizes, surface brightnesses, and velocity dispersions. Measuring observable properties allows distance estimation through this empirical relation. These secondary distance indicators extend measurements to cosmological distances, where primary indicators like Cepheids cannot be observed. The systematic uncertainties in distance measurements propagate through the cosmic distance ladder. Errors in nearby distance measurements affect calibration of more distant indicators. The Hubble tension partly reflects this uncertainty propagation. Different teams analyzing the same data can reach slightly different conclusions based on how they handle systematic effects. Reducing these uncertainties requires identifying and correcting subtle biases in observations and analysis. The cosmic expansion affects biological evolution in subtle ways. The changing radiation environment as stars evolve influences mutation rates. The availability of heavy elements created by previous star generations affects what chemistry is possible. The expansion timescale sets how long stable environments persist. These effects are indirect but genuine connections between cosmic expansion and life's development. The rare Earth hypothesis suggests that while simple life might be common, complex life requiring many specific conditions might be extremely rare. The expansion rate is one of many factors that must fall in narrow ranges for complex life to develop. Too fast, and stellar lifetimes are too short for evolution. Too slow, and the universe recollapses before complexity emerges. This suggests Earth-like planets might be uncommon in the universe. The Drake equation attempts to estimate the number of technological civilizations in our galaxy by multiplying probabilities for various factors, like star formation rate, planet occurrence, and probability of life developing. The expansion of space doesn't directly appear in this equation, but it affects the background conditions, making some of these factors more or less probable. The accelerating expansion will eventually isolate our galaxy, limiting the region where future civilizations could ever communicate with us. The Fermi paradox becomes even more puzzling when considering cosmic expansion. If civilizations commonly develop and spread across galaxies, we should see evidence of them. The expansion of space doesn't resolve this paradox, since our galaxy and nearby galaxies aren't carried apart by expansion due to gravitational binding. The puzzle of why we see no evidence of alien civilizations remains. The Great Filter hypothesis suggests that some step in the development from non-living matter to spacefaring civilization is extremely unlikely. This filter could be behind us, perhaps in the origin of life or development of intelligence, or ahead of us, perhaps in avoiding self-destruction. If the filter is ahead, this has sobering implications for humanity's future. Cosmic expansion doesn't directly address where the filter might be, but it sets the timeline over which life can develop. The expansion of space influences how we think about humanity's long-term future. If we survive, we face eventual resource limitations as stars die. Cosmic expansion makes colonizing other galaxy clusters impossible, limiting where humanity could potentially spread. These constraints are far in the future, but they represent ultimate limits on civilization's scope. The concept of Dyson spheres, hypothetical structures that would capture a star's entire energy output, has been proposed as something advanced civilizations might build. Searching for infrared signatures of such structures provides one way to look for alien intelligence. The expansion of space doesn't prevent building Dyson spheres within gravitationally bound systems, but it does limit how many star systems could ever be reached for colonization. The expansion of space connects to questions about consciousness and its place in the universe. Some theories propose that consciousness is fundamental rather than emergent, perhaps related to quantum mechanics or information processing. If consciousness is fundamental, its relationship to expanding spacetime raises deep questions. Does consciousness require physical substrates that can only exist during certain cosmic epochs? These questions lie at the boundary between physics and philosophy. The hard problem of consciousness asks why subjective experience exists rather than just objective information processing. Physics describes the objective structure and dynamics of reality, but doesn't obviously explain subjective experience. Whether understanding cosmic expansion and its quantum mechanical origins could shed light on consciousness remains highly speculative. The simulation hypothesis suggests we might exist in a computer simulation run by an advanced civilization. If true, cosmic expansion might be a feature of the simulation rather than fundamental physics. However, this hypothesis is unfalsifiable with current methods and raises the question of what physics governs the simulator's reality. Most physicists treat it as an interesting philosophical idea rather than a scientific hypothesis. The mathematical universe hypothesis proposes that physical reality is mathematics, not just described by mathematics. In this view, all mathematical structures exist as physical realities, and we inhabit one particular structure. Cosmic expansion would be a feature of the specific mathematical structure that is our universe. This idea attempts to explain why mathematics describes physics so well, but raises questions about what it means for mathematics to exist. The expansion of space ultimately returns us to wonder and humility. We've learned an extraordinary amount about how the universe evolves, yet fundamental questions remain unanswered. The nature of dark matter and dark energy, the resolution of the Hubble tension, the ultimate fate of the universe, all await future discoveries. Each answer will likely reveal new questions, as has happened throughout scientific history. The process of discovery continues. New telescopes observe with unprecedented sensitivity. Gravitational wave detectors open new windows on the cosmos. Particle physics experiments search for dark matter. Theoretical work develops new models and calculates their predictions. The community of scientists worldwide collaborates on understanding cosmic expansion and its implications. The expansion of space teaches us about the nature of scientific knowledge. We build understanding through observation and theory, constantly testing and refining our models. We accept that some questions might be unanswerable, that nature might keep some secrets forever. Yet we continue investigating what we can learn, driven by curiosity about how reality works. Your existence during this cosmic epoch is both cosmically insignificant and personally meaningful. The universe is vast and old, and you occupy a tiny portion of space-time. Yet you possess consciousness, the capacity to understand the cosmos and contemplate your place in it. Through you and other conscious beings, the universe develops self-awareness. This remains remarkable regardless of cosmic scales. The atoms in your body have cosmic histories. Carbon was forged in stars. Oxygen came from massive stars that exploded as supernovae. Iron was created in supernova cores. These atoms travelled through space, incorporated into nebulae that collapsed to form new stars and planets. Eventually they assembled into living cells, then complex organisms, then you. Your physical substance connects you to cosmic history spanning billions of years and countless light years. The expansion of space carried those atoms through the cosmos during their journey. The same force that carries galaxies apart also influenced the paths atoms took before forming you. You are literally made of stardust carried across expanding space by cosmic evolution. This poetic description is also literal scientific truth. The future of cosmic expansion will unfold over timescales that dwarf human history. Stars will continue shining for trillions of years. Black holes will evaporate over times requiring more than 60 digits to express in years. The universe will expand toward heat death over even longer timescales. Yet all of this remains knowable to us now through the power of physics and mathematics. We can predict cosmic evolution far into the future because physical laws appear unchanging. The same equations describing expansion today should apply billions of years hence. This predictive power represents one of science's greatest achievements. We transcend our temporal limitations through understanding, seeing far beyond our brief moment in cosmic time. The expansion of space will continue its inexorable course regardless of human concerns. We cannot stop it, cannot control it, cannot change it. We can only observe, measure, and understand. This powerlessness might seem discouraging, yet it also liberates. We need not worry about cosmic expansion on human timescales. It proceeds so slowly at local scales that it has no practical impact on human affairs. Yet understanding cosmic expansion enriches human knowledge and perspective. We know our place in a vast, evolving universe. We understand how that universe began and how it will end. We've learned this through centuries of careful observation and theoretical work. This knowledge represents a genuine achievement of human intelligence and curiosity. The cosmos is vast beyond human comprehension, existing for times longer than human minds can grasp, yet we've decoded its essential dynamics. From observations of distant galaxies and the cosmic microwave background, we've reconstructed cosmic history. We've determined the universe's age, composition, and fate. We've discovered that space itself expands, carrying everything with it toward an uncertain but calculable future. This knowledge transforms how we understand existence. We're not separate from the cosmos observing it from outside. We're part of cosmic evolution, made of atoms processed through stellar furnaces, organized into complex structures by the same forces shaping galaxies. Our consciousness represents the universe's capacity for self-reflection. Through science, the cosmos knows itself. The expansion of space provides perspective on human concerns. The problems facing humanity, while serious from our perspective, are cosmically insignificant. Climate change, political conflicts, economic challenges, all these unfold against a cosmic backdrop that dwarfs them. This perspective might seem to diminish human concerns, but it can also focus attention on what matters. We have limited time to address challenges before opportunities pass. The accelerating expansion means that resources beyond our local group will eventually become inaccessible. If humanity survives long enough to become a spacefaring civilization, we'll be confined to our gravitationally bound region. This creates urgency about how we use resources in our cosmic neighborhood. We cannot count on accessing matter and energy from distant galaxy clusters. The expansion of space also creates opportunities for long-term thinking. Understanding cosmic timescales helps us plan for the far future. If we survive the next few centuries of technological and environmental challenges, we face an enormous future stretching billions of years. How should long-lived civilizations approach existence, knowing the universe will eventually reach heat death? These questions blend science with philosophy and ethics. The possibility of cosmic engineering, manipulating matter and energy on astronomical scales, raises fascinating questions. Could sufficiently advanced civilizations harvest energy from stars or black holes to survive longer than natural processes would allow? Could they travel between gravitationally bound galaxy clusters before expansion separates them? These speculations extend far beyond current capabilities, but are not prohibited by known physics. The expansion of space ultimately represents one aspect of a universe that exists independent of human observation. Before humans evolved, galaxies receded from each other. They'll continue receding long after humans are gone. The universe doesn't need observers to expand. It follows physical laws automatically. We're fortunate to exist during an epoch when we can study and understand these laws. The scientific method that revealed cosmic expansion represents humanity's most powerful tool for understanding reality. By making observations, forming hypotheses, testing predictions, and revising theories, we've built reliable knowledge about nature. This process works because reality has consistent, discoverable structure. The same physical laws apply throughout space and time, allowing us to understand distant regions and predict future evolution. The expansion of space exemplifies how science progresses. Initial observations by Hubble revealed recession velocities. Einstein's theory provided the framework for understanding this as space expansion. Subsequent observations confirmed and refined the picture, discovering cosmic acceleration and constraining dark energy properties. Each generation of scientists built on previous work, accumulating knowledge that now spans nearly a century of research. Future generations will continue this work. They'll measure expansion rates with greater precision. They'll probe dark energy's nature with better instruments. They'll test general relativity in new regimes. They might discover new physics we haven't imagined, or they might confirm that our current understanding is essentially correct, just requiring refinement around the edges. The history of science shows both possibilities occur. Sometimes new observations overturn prevailing theories, as cosmic acceleration overturned expectations of deceleration. Other times, observations confirm existing theories with increasing precision, as happened with many. General relativity tests. Both outcomes advance knowledge by either revealing new phenomena or constraining possibilities more tightly. The expansion of space connects to fundamental questions about reality that might never be fully answered. Why does anything exist? Why do physical laws have their particular mathematical form? Why is the universe comprehensible to human minds? These questions push beyond empirical science into philosophy and perhaps beyond what can be known. Yet the questions we can answer are themselves profound. We know the universe expands. We know its age and composition. We understand its large-scale structure and evolution. We can predict its future across timescales that dwarf its current age. This knowledge represents a triumph of human reason and observation over cosmic mystery. The wonder of cosmic expansion lies not just in the facts themselves, but in our capacity to discover them. conscious beings emerged on a rocky planet orbiting an average star, developing intelligence sufficient to understand cosmic evolution. This emergence of understanding from unconscious matter represents perhaps the deepest mystery of all. How does consciousness arise? Why does the universe contain beings capable of comprehending it? These questions about consciousness and its cosmic role remain largely unanswered. Neuroscience explains much about how brains work, but the relationship between neural activity and subjective experience remains mysterious. Whether consciousness requires specific physical substrates or might be more fundamental remains debated. The expansion of space provides the backdrop against which conscious beings evolved, but the connection between cosmic expansion and consciousness is unclear. The anthropic considerations mentioned earlier suggest our existence places constraints on what we can observe about cosmic expansion. We necessarily find ourselves in a universe where expansion permits structure formation and biological evolution. This selection effect might explain some apparent cosmic coincidences, yet it doesn't explain why any universe exists or why physical laws permit consciousness. The expansion of space will outlast all conscious observers if current cosmology is correct. Eventually, the universe will cool and dilute until no life can survive. The capacity for understanding that briefly emerged during the stellar era will fade away. This might seem tragic, yet it's simply how physical processes work. Conscious understanding represents a temporary phenomenon in cosmic evolution. Yet that temporary phenomenon is real and meaningful while it lasts. The fact that understanding will eventually cease doesn't negate its current value. You exist now, capable of contemplating cosmic expansion. This capacity has worth regardless of its duration. Meaning doesn't require permanence. The expansion of space teaches us humility about our place in the cosmos, while also revealing the power of human reason. We're insignificant on cosmic scales, yet we've understood profound truths about reality. This combination of humility and accomplishment characterizes the human relationship with the universe. We're small but capable of understanding vastness. The journey through cosmic expansion ends where it began, with space itself growing. Every second the fabric of reality stretches, increasing distances between galaxy clusters. This expansion started 13.8 billion years ago and will continue indefinitely into the future. It affects everything on sufficiently large scales while having no practical impact on human daily life. It reveals the universe's dynamic nature and connects us to cosmic history spanning billions of years. Understanding cosmic expansion represents one of humanity's greatest intellectual achievements. From ancient people wondering about stars to modern cosmologists measuring dark energy, the path of discovery spans millennia. Each generation contributed observations and insights that accumulated into our current understanding. We stand on the shoulders of countless researchers who dedicated their lives to comprehending the cosmos. The expansion of space continues whether we observe it or not, whether we understand it or not. The universe evolves according to physical laws that operate independently of human concerns. Yet we've achieved something remarkable by figuring out these laws and understanding cosmic evolution. Through science, we've connected our brief lives to the vast sweep of cosmic history. We've learned where we came from, where we're going, and how it all works. This knowledge enriches human existence and demonstrates what consciousness can achieve. The universe expands, and we expand our understanding along with it, reaching across billions of light years and billions of years to comprehend reality's deepest structures. This is the story of cosmic expansion, a story of space, time, matter, energy, and the conscious beings who learn to understand it all. Space itself is growing. Right now, at this very moment, the distance between distant galaxies increases by thousands of miles every single second. This isn't science fiction or speculation. This is the measured, observed reality of our universe. Every cubic inch of space stretches like an invisible fabric being pulled in all directions at once. The universe expands, and this expansion represents one of the most profound discoveries in human history. Understanding cosmic expansion requires us to fundamentally rethink what we mean by space itself. Most of us think of space as simply emptiness, the void between objects where nothing exists. But modern physics reveals something far stranger. Space is not nothing. Space is a physical entity with measurable properties. It can bend, ripple, and most remarkably, it can grow. When we say the universe expands, we don't mean that galaxies fly apart through static, unchanging space like debris from an explosion. We mean that space itself stretches, carrying galaxies along with it, like raisins in rising bread dough. This distinction matters enormously. If galaxies simply moved through space, they would be limited by the cosmic speed limit set by Einstein's theory of relativity. Nothing with mass can travel through space faster than light, which moves at approximately 186,000 miles per second. But space itself faces no such restriction. Space can grow as fast as physical law allows, and at sufficiently large distances, this growth carries galaxies away from us faster than light itself can. Travel. This sounds impossible, but it's the direct consequence of space expansion, and we observe it happening throughout the cosmos. To visualize how this works, imagine drawing dots on the surface of a balloon to represent galaxies, then slowly inflating the balloon. As the rubber stretches, every dot moves away from every other dot. Crucially, the dots themselves don't move across the rubber surface. The rubber carries them along as it expands. From any single dot's perspective, all other dots appear to recede in every direction. The dot that started farther away ends up moving faster because there's more rubber between them to stretch. This is precisely how cosmic expansion works, just extended into 3 dimensions instead of the balloon's 2-dimensional surface. The expansion of space was discovered almost by accident. In the 1920s, most astronomers believed the universe was static and eternal, unchanging on cosmic scales. Even Albert Einstein, whose equations of general relativity actually predicted a dynamic universe, modified his theory with a mathematical term he called the cosmological constant, specifically to keep the universe static. He later called this his greatest blunder. The universe, it turned out, had other plans. Edwin Hubble, working with the world's most powerful telescope at Mount Wilson Observatory in California, made observations that changed everything. He studied galaxies beyond our own Milky Way, measuring their distances and velocities with unprecedented precision. What he discovered in 1929 shocked the scientific world. Every galaxy he observed was moving away from us. Not just moving away, but moving away in a very specific pattern. The farther away a galaxy was, the faster it receded. Double the distance, and the recession velocity doubled as well. This simple linear relationship became known as Hubble's law, and it provided the first direct evidence that the universe itself was expanding. Hubble measured galaxy velocities using a technique based on the Doppler effect, but applied to light instead of sound. When an ambulance approaches you, its siren sounds higher pitched because the sound waves get compressed. When it moves away, the pitch drops as the waves stretch out. Light behaves similarly. When a galaxy moves away from us, the light waves stretch to longer, redder wavelengths. This redshift allows astronomers to calculate precisely how fast a galaxy recedes. Hubble found that distant galaxies showed greater redshift, indicating higher recession velocities proportional to their distance. The implications were staggering. If everything moves away from everything else now, then logically, everything must have been closer together in the past. Trace this expansion backward in time, and you arrive at a moment when all matter and energy in the universe occupied the same point. This moment, approximately 13.8 billion years ago, marks what we now call the Big Bang, the beginning of space and time as we understand them. The Big Bang was not an explosion in space. This common misconception leads to confused thinking about cosmic expansion. There was no empty space that existed before the Big Bang into which matter exploded. Space itself came into existence with the Big Bang. The expansion is not matter flying outward through pre-existing space, but rather space itself growing larger, carrying matter along for the ride. This means the Big Bang happened everywhere at once, because every point in space today was compressed into the initial singularity. There is no center to the expansion, no special location where the Big Bang occurred. It happened at every point simultaneously. Current measurements tell us the universe is 13.8 billion years old, give or take about 20 million years. This age is determined through multiple independent methods that all converge on the same answer. We can measure the expansion rate today and calculate backward to when everything was compressed to a point. We can study the oldest stars and determine their ages through nuclear physics. We can analyze the cosmic microwave background radiation, the afterglow of the Big Bang itself, which provides a snapshot of the universe when it was only 380,000 years old. All these methods agree on the universe's age to remarkable precision. The expansion rate itself is quantified by the Hubble constant, named after Edwin Hubble. This constant tells us how fast space expands at different distance scales. Current measurements suggest that for every megaparsec of distance, which equals approximately 3.3 million light-years, space expands by about 70 kilometers per second. This means that a galaxy located 1 megaparsec away recedes at 70 kilometers per second. A galaxy twice as far away recedes at 140 kilometers per second. A galaxy 10 times farther recedes at 700 kilometers per second, and so on. At sufficiently large distances, this linear relationship produces recession velocities that exceed the speed of light. A galaxy located about 14 billion light-years away recedes at approximately the speed of light itself. Galaxies farther than this recede faster than light, not because they move through space faster than light, which would be impossible, but because the space between us and them expands so rapidly that the total recession velocity exceeds light speed. This creates a cosmic horizon beyond which we cannot see, because light from those regions can never reach us. The light travels toward us at its maximum speed, but space expansion carries the source away faster than the light can make up the distance. This cosmic horizon is not fixed. As time passes and the universe continues expanding, the horizon moves outward, revealing new regions of space. However, cosmic expansion doesn't just proceed at a steady rate. Recent observations have revealed something unexpected and deeply puzzling. The expansion is accelerating. Distant supernovae appear dimmer than they should be if expansion were constant or slowing down. This dimness indicates they're farther away than expected, meaning something has accelerated the expansion, carrying them to greater distances than simple models predict. This acceleration was discovered in 1998 by two independent teams of astronomers studying Type Ia supernovae. These stellar explosions serve as cosmic distance markers because they all explode with nearly identical brightness. By comparing their apparent brightness to their known absolute luminosity, astronomers can calculate exact distances. When they plotted these distances against redshift measurements, expecting to find that cosmic expansion was gradually slowing down due to gravity, they instead found the opposite. Expansion was speeding up. This discovery earned the team leaders the Nobel Prize in Physics and introduced one of the greatest mysteries in modern science: dark energy. Dark energy is the name we give to whatever causes cosmic acceleration. The name reflects our profound ignorance about its nature. We cannot see it, cannot touch it, cannot detect it with any instrument except through its gravitational effects on cosmic expansion. Yet this invisible, mysterious entity dominates the universe. Current observations suggest that dark energy accounts for approximately 68% of the total energy density of the universe. Ordinary matter, everything made of atoms including all stars, planets and living beings, comprises less than 5%. Another mysterious component called dark matter makes up about 27%. This means that 95% of the universe consists of things we fundamentally do not understand. Dark energy appears to be uniformly distributed throughout space with constant density. Unlike matter, which clumps together into galaxies and clusters, dark energy shows no variation from one region to another. Even more puzzling, as the universe expands and space grows larger, the total amount of dark energy increases proportionally. Double the volume of space, and you apparently double the amount of dark energy. This seems to violate energy conservation, one of physics' most fundamental principles, though the situation is more subtle than simple violation. The leading explanation for dark energy suggests it represents the energy of empty space itself, arising from quantum mechanical effects. Quantum physics predicts that what we call empty space actually seethes with virtual particles that pop into existence and vanish again in incredibly brief moments. These quantum fluctuations might create a baseline energy density throughout space. However, when physicists calculate what this quantum vacuum energy should be, they get an answer that exceeds observations by a factor of 10 to the power of 120. This represents the worst prediction in the history of physics, suggesting either our quantum theory is fundamentally wrong or dark energy has a completely different origin. Alternative theories propose that dark energy emerges from modifications to general relativity on cosmic scales, from extraspatial dimensions beyond the three we perceive, or from a dynamical field that changes over time rather than remaining constant. Recent observations from the Dark Energy Spectroscopic Instrument, known as DESI, have detected hints that dark energy might indeed evolve over cosmic time. If confirmed, this would require entirely new physics to explain and would dramatically alter predictions about the universe's ultimate fate. The nature of cosmic expansion becomes even more intriguing when we consider its effects at different scales. At the scale of atoms, molecules, and even human bodies, expansion has absolutely no effect. The electromagnetic forces holding atoms together and the chemical bonds linking molecules are vastly stronger than the weak gravitational effects driving cosmic expansion. Your body does not expand with the universe because the forces keeping you intact easily overcome any expansion effects. Similarly, Earth's orbit around the Sun remains stable despite cosmic expansion. The Sun's gravitational pull keeps Earth in its orbit, and this gravitational binding is millions of times stronger than expansion effects at solar system scales. Even our entire Milky Way galaxy, spanning about 100,000 light-years and containing roughly 400 billion stars, maintains its size and structure. Gravity binds the galaxy together far more strongly than expansion can pull it apart. Galaxy clusters, the largest gravitationally bound structures in the universe, also resist expansion. These massive collections of hundreds or thousands of galaxies, spanning about 10 million light-years, stay bound together through their collective gravitational attraction. Only at scales larger than galaxy clusters does cosmic expansion dominate over gravity. The vast spaces between different galaxy clusters grow continuously as expansion overwhelms the relatively weak gravitational attraction between these distant structures. This selective effect of expansion creates a cosmic landscape of gravitationally bound islands in an expanding ocean. Galaxy clusters remain intact, while the empty space between them grows. As expansion accelerates due to dark energy, these islands become increasingly isolated. Eventually, galaxy clusters will drift so far apart that galaxies in one cluster will no longer be visible from another. Each cluster will become a cosmic island universe, completely isolated from all others. The expansion of space creates another remarkable phenomenon that allows us to look backward through cosmic history. Light traveling through expanding space gets stretched along with the space itself. This stretching increases the wavelength of light, shifting it toward the red end of the spectrum. The amount of this cosmological redshift directly reveals how much the universe has expanded during the light's journey. A redshift value of 1 means the universe has doubled in size since the light was emitted. A redshift of 2 indicates the universe has tripled in size. The most distant galaxies we observe show redshifts exceeding 10, meaning the universe has grown more than 11 times larger since their light began traveling toward us. This cosmological redshift differs fundamentally from the Doppler redshift caused by motion through space. Doppler redshift occurs because a moving source compresses or stretches light waves as they're emitted. Cosmological redshift occurs because space itself expands during the light's journey, stretching the waves like marks on a rubber band being pulled. Both effects look similar when we observe them, but they arise from completely different physical processes. The most extreme redshift we can observe comes from the cosmic microwave background radiation. This ancient light was emitted when the universe was only 380,000 years old, at a moment astronomers call recombination. Before this moment, the universe was so hot and dense that electrons could not bind to atomic nuclei. Free electrons scattered light in all directions, making space completely opaque, like trying to see through fog. Then the universe cooled enough for electrons to combine with protons and helium nuclei, forming the first stable atoms. Suddenly, light could travel freely through space. The universe became transparent, and this moment of cosmic transparency occurred simultaneously throughout all of space. The light emitted at recombination has been traveling through space for 13.4 billion years. During this journey, cosmic expansion has stretched it by a factor of about 1,100. Light that was originally emitted as visible and infrared radiation now arrives as microwave radiation, with wavelengths measured in millimeters. This cosmic microwave background fills the entire sky with uniform radiation at a temperature of about 2.7 degrees above absolute zero, negative 454 degrees Fahrenheit. The cosmic microwave background appears remarkably uniform in all directions, varying in temperature by only about 1 part in 100,000 across the entire sky. This uniformity initially puzzled astronomers because it required regions of space separated by billions of light years to have identical temperatures and properties. Yet these regions could never have communicated with each other traveling at light speed. How did distant regions reach the same temperature if they couldn't exchange energy? The answer lies in cosmic inflation, one of the most important developments in cosmology since the discovery of expansion itself. Inflation theory, proposed by Alan Guth in 1980, suggests that during the first tiny fraction of a second after the Big Bang, space expanded exponentially faster than light could travel. In less than a trillionth of a trillionth of a trillionth of a second, the universe grew by a factor larger than 10 to the power of 26. This incredible expansion stretched tiny regions that were in thermal equilibrium to cosmic proportions, explaining why the universe appears so uniform today. Inflation also explains another puzzling feature of our universe, its geometric flatness. Space can curve in different ways, like how a piece of paper can be bent into various shapes. General relativity allows three possibilities. Space could curve positively like the surface of a sphere, curve negatively like a saddle, or remain flat like an infinite sheet. Observations show that our universe is flat to within about 1% accuracy. This flatness appears to be an incredible cosmic coincidence because any initial curvature should have been amplified by expansion. Inflation solves this by stretching any initial curvature until it becomes undetectable, just like inflating a balloon until its surface appears flat. The tiny temperature fluctuations in the cosmic microwave background, though small, are crucially important. These variations represent quantum fluctuations from the early universe that inflation stretched to cosmic scales. Slightly warmer regions contained slightly more matter and energy. Over millions and billions of years, gravity amplified these tiny density differences. Matter flowed into the denser regions, forming the first stars, galaxies, and eventually the large-scale structure of galaxy clusters and cosmic filaments we observe today. Every galaxy, every star, every planet traces its origin to microscopic quantum fluctuations in the first instance after the Big Bang. Computer simulations can recreate this cosmic evolution. Starting from the tiny density variations seen in the cosmic microwave background and applying the laws of gravity and hydrodynamics, astronomers simulate how matter clumps and evolves over billions of years. These simulations reproduce the observed large-scale structure of the universe with remarkable accuracy, providing strong evidence that we understand the basic processes driving cosmic evolution. Dark matter plays a crucial role in this structure formation. Although dark matter remains mysterious, we know it interacts primarily through gravity. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Yet its gravitational influence shapes cosmic structure. Dark matter forms the scaffolding on which visible matter arranges itself. Dark matter halos surround galaxies, providing the gravitational wells that hold them together. Dark matter filaments connect galaxy clusters across vast distances, channeling matter along cosmic superhighways. Without dark matter, galaxies couldn't have formed as quickly as we observe. The gravitational attraction of ordinary matter alone wouldn't have been strong enough to overcome cosmic expansion and pull gas clouds together to form the first stars within the first few 100 million years after the Big Bang. Dark matter's additional gravity was necessary to jumpstart structure formation. Computer simulations that omit dark matter fail to produce anything resembling the universe we observe. Several candidates have been proposed for dark matter particles. Weakly interacting massive particles, called WIMPs, represent the leading candidate. These hypothetical particles would interact only through gravity and the weak nuclear force, making them extremely difficult to detect. Despite decades of searches using increasingly sensitive detectors, WIMPs have not been conclusively observed. Other candidates include axions, sterile neutrinos, and primordial black holes formed in the early universe. Each possibility has different implications for how dark matter affects cosmic expansion and structure formation. The interplay between dark matter and dark energy creates a cosmic competition that determines the universe's fate. Dark matter tries to pull things together through gravity, building larger structures. Dark energy pushes things apart, accelerating expansion. In the early universe, dark matter dominated, and structure formation proceeded rapidly. About 5 billion years ago, dark energy became dominant, and expansion began accelerating. As expansion accelerates, it becomes increasingly difficult for gravity to pull new structures together. Eventually, dark energy will completely halt structure formation, leaving the universe with the structures that already exist while carrying them ever farther apart. This brings us to one of the most perplexing problems in modern cosmology: the Hubble tension. Two completely independent methods for measuring the expansion rate produce different answers. The disagreement is small, only about 9%, but both methods achieve precision better than 2%. The discrepancy far exceeds the measurement uncertainties, indicating something is fundamentally wrong with our understanding. One method analyzes the cosmic microwave background radiation. By studying the pattern of temperature fluctuations in exquisite detail, cosmologists can determine the expansion rate the universe had when this light was emitted. Using our best models of how expansion has evolved over cosmic time, including the effects of matter, radiation, and dark energy, they calculate what the expansion rate should be today. This method yields a Hubble constant of about 67 kilometers per second per megaparsec. The second method measures distances to nearby galaxies using pulsating stars, called Cepheid variables. These stars change brightness in regular cycles directly related to their absolute luminosity. By comparing apparent brightness to known luminosity, astronomers calculate precise distances. Combined with redshift measurements, this gives a direct measurement of the expansion rate in our local cosmic neighborhood. This method yields a Hubble constant of about 73 kilometers per second per megaparsec. The 6-unit difference between these values has persisted, despite intensive efforts to find systematic errors in either method. Multiple independent techniques confirm both measurements. The cosmic microwave background analysis has been verified by the Planck satellite and other missions. The local distance measurements have been confirmed using different types of variable stars, supernova observations, and gravitational lensing. The tension is real. Adam Rees, who shared the Nobel Prize for discovering dark energy acceleration, leads the team making local measurements. The James Webb Space Telescope, the most powerful observatory ever built, has provided new data that confirms the local measurements with unprecedented precision. Webb can observe Cepheid variables in galaxies up to 130 million light-years away, studying over 300 of these distance markers. The results agree with previous local measurements to within 1%, eliminating most remaining doubt about systematic errors. The Hubble tension suggests that our standard model of cosmology is incomplete. Perhaps dark energy behaved differently in the past than our models assume. Maybe unknown particles influenced expansion during the universe's first few billion years. Some theories propose that space itself has properties we haven't discovered. The tension might even indicate that general relativity needs modification on cosmic scales. Resolving this tension is crucial because the Hubble constant determines fundamental cosmic parameters. It affects calculations of the universe's age, the distances to galaxies, and predictions about the ultimate fate of expansion. If we cannot measure this fundamental parameter correctly, our entire cosmological framework stands on uncertain ground. Every point in space experiences expansion identically, creating a situation where every observer believes they sit at the universe's center while there is actually no center at all. This centerless expansion represents one of the most counterintuitive aspects of cosmology. When you look out at distant galaxies, they all recede from you in every direction. You appear to occupy a special position at the center of cosmic expansion. But if you could instantly travel to any of those distant galaxies and look around, you would see exactly the same pattern. All other galaxies would recede from your new location in every direction. That galaxy would also appear to be at the expansion center. This happens because expansion affects all of space uniformly. There is no preferred location, no special cosmic address. The expansion has no center for the same reason it has no edge. If the universe is infinite, then every point in infinite space participates equally in expansion. If the universe is finite but curved back on itself like the surface of a sphere, then there's still no center within the space itself, just as the surface of a sphere has no special central point on the surface. The Big Bang did not happen at a particular location in space. It happened everywhere simultaneously because all of space was compressed to a point. As expansion began, every point in space moved away from every other point. There was no cosmic explosion from a central location hurling debris outward. Space itself grew larger, carrying matter with it. This is why we can observe the cosmic microwave background radiation coming from all directions. That ancient light was emitted throughout all of space when the universe became transparent. We see it coming from every direction because every point in space participated in that moment. Understanding expansion without a center requires thinking carefully about what expansion means. When we say the universe expands, we don't mean stuff spreads out through pre-existing space. We mean the measuring stick of space itself grows larger. Imagine a coordinate grid with galaxies at various grid points. Expansion doesn't move the galaxies to different grid points. Instead, the grid squares themselves grow bigger, increasing the distance between grid points while the galaxies remain at their same coordinates. Mathematicians call this intrinsic expansion rather than extrinsic expansion. Extrinsic expansion would mean the universe grows into something external to itself, like a balloon expanding into the surrounding room. Intrinsic expansion means space grows within itself, creating more space without requiring anything external. Our three-dimensional space expands intrinsically, becoming larger without needing a fourth spatial dimension to expand into. This creates a profound philosophical puzzle. If the universe expands into nothing, what does expansion even mean? The answer lies in recognizing that expansion is fundamentally about changing distances. The separation between galaxies increases over time. This change is real and measurable, even though there's no external reference frame. Distance itself becomes a dynamic property of space rather than a fixed relationship between objects. The observable universe, the region from which light has had time to reach us, has a finite size despite the universe itself potentially being infinite. Light travels at a finite speed, and the universe has a finite age, so we can only see a finite distance. This creates a cosmic horizon centered on Earth, beyond which we cannot observe anything. The observable universe has a radius of about 46 billion light-years, containing everything we can possibly detect. You might expect the observable universe to have a radius of only 13.8 billion light-years, matching the universe's age. Light has been traveling for 13.8 billion years, so shouldn't it have traveled only 13.8 billion light-years? The actual radius is larger because space expansion carried the sources of the oldest light farther away while the light was traveling. When that light was emitted, the sources were much closer than 46 billion light-years away, but 13.8 billion years of expansion have carried them to their current distance. This observable universe is centered on Earth only because we're doing the observing from Earth. Every other galaxy has its own observable universe centered on it. These observable regions overlap, but they're not identical. Galaxies very far from us can see regions we cannot, and vice versa. If the universe is truly infinite, then each observable universe represents an infinitely small fraction of total reality. As expansion accelerates, our observable universe actually shrinks in terms of the number of galaxies it contains. The cosmic horizon moves outward, but distant galaxies recede faster than the horizon expands. More galaxies cross the horizon into unobservability than enter from beyond. In the far future, assuming dark energy remains constant, only our local group of gravitationally bound galaxies will remain visible. All other galaxies will have vanished beyond the horizon. Future astronomers will see a much lonelier cosmos, unable to detect evidence of the billions of galaxies we observe today. The regions beyond our cosmic horizon might contain remarkable things. If the universe is infinite, then infinite regions exist that we can never observe. These unreachable domains might contain copies of ourselves living identical lives, simply because probability theory suggests that any finite arrangement of particles must repeat given infinite space. Somewhere beyond the horizon might exist planets exactly like Earth, orbiting stars exactly like our Sun, populated by people living lives identical to yours. The math of infinite space virtually guarantees such duplicates, though we could never verify or communicate with them. The expansion of space also has profound implications for light traveling across cosmic distances. As space stretches, it stretches light waves traveling through it. This cosmological redshift provides our primary tool for measuring cosmic distances and expansion rates. The amount of redshift reveals how much the universe has expanded since the light was emitted. High redshift indicates the light comes from early cosmic times when the universe was much smaller. The James Webb Space Telescope was specifically designed to observe in infrared wavelengths because it targets the most distant galaxies with extreme redshifts. These ancient galaxies emitted their light in ultraviolet and visible wavelengths, but cosmic expansion has stretched this light into the infrared. Webb's infrared vision allows it to peer farther into the past than any previous telescope, observing galaxies as they appeared when the universe was only a few 100 million years old. These ancient galaxies appear remarkably well developed given their youth. Some contain billions of stars and show evidence of supermassive black holes in their centers. This rapid development challenges models of structure formation, suggesting that galaxy assembly began even earlier than previously thought, or proceeded more efficiently than simulations predict. The early universe was apparently busier and more dynamic than our models anticipated. Studying these distant galaxies provides direct tests of expansion models. Different expansion histories predict different relationships between redshift and distance. By measuring both quantities for large samples of galaxies at various distances, astronomers can determine how the expansion rate has changed over cosmic time. These observations confirmed that expansion was initially slowing down due to gravity, but began accelerating about 5 billion years ago as dark energy became dominant. The ultimate fate of cosmic expansion depends critically on the nature of dark energy. If dark energy remains constant, as current observations suggest, then expansion will continue accelerating forever. The universe will grow exponentially larger over time, eventually isolating every gravitationally bound structure. Galaxy clusters will drift beyond each other's horizons. Eventually, even galaxies within clusters will scatter as dark energy overcomes their gravitational binding. The universe will become increasingly cold, dark, and empty as expansion dilutes all forms of energy. This heat death scenario predicts that star formation will cease when the universe is about 100 times its current age. After this point, no new stars will form because expansion has spread matter too thinly for gravity to collapse gas clouds. Existing stars will continue burning until their fuel exhausts, but no new generations will replace them. The era of stars, the epoch that makes the universe interesting and habitable, represents a brief moment in cosmic history. After stars die, they leave behind white dwarfs, neutron stars, and black holes. These remnants will cool over timescales that dwarf the current age of the universe. White dwarfs, the dense cores of sun-like stars, will cool and fade over trillions of years. Neutron stars will take even longer. Black holes will survive longest, but even they face ultimate evaporation through Hawking radiation. Stephen Hawking discovered that black holes aren't entirely black. Quantum effects near the event horizon cause black holes to emit radiation, slowly losing mass. A black hole with the Sun's mass would take about 10 to the 67th power years to evaporate completely. Supermassive black holes would require time so long that expressing the number of years would take thousands of digits. Yet given enough time, even these will evaporate, leaving behind only elementary particles scattered across exponentially expanding space. The final state of the universe, assuming constant dark energy, is a cold, empty expanse approaching absolute zero temperature, with particles so far apart they rarely interact. This represents maximum entropy, the state of ultimate cosmic disorder where no gradients exist and no work can be performed. The universe will have exhausted all its potential for interesting events. This heat-death scenario describes a universe that expands forever into increasing darkness and cold. However, if dark energy strengthens over time, the fate could be even more dramatic. Strong enough dark energy could eventually overcome all forces, including those holding atoms together. This Big Rip scenario would tear apart galaxy clusters first, then galaxies, then solar systems, then planets, and ultimately atoms themselves. Everything would be ripped apart by accelerating expansion. Current observations don't strongly favor this scenario, but we cannot rule it out. Alternatively, if dark energy weakens or reverses, expansion could slow and eventually halt. The universe might then begin contracting, with all matter falling back together in a big crunch. This would create a mirror image of the Big Bang, with the universe collapsing to a singularity. Some models suggest the Big Crunch could trigger a new Big Bang, creating an endless cycle of cosmic expansion and contraction. However, current observations showing acceleration make this scenario seem unlikely unless dark energy behaves very differently in the future than it does today. Recent observations from the Dark Energy Spectroscopic Instrument hint that dark energy might evolve over time rather than remaining constant. If confirmed, this would open new possibilities for the universe's future that don't fit neatly into heat death, Big Rip, or Big Crunch scenarios. Evolving dark energy could lead to complex future dynamics we haven't yet imagined. The expansion of space connects to quantum mechanics in ways we're only beginning to explore. Quantum field theory suggests that empty space constantly produces virtual particle pairs that appear and disappear in incredibly brief instants. These quantum fluctuations might be related to dark energy, though as mentioned earlier, naive calculations produce wildly incorrect predictions. Understanding this connection between quantum mechanics and cosmic expansion represents one of the deepest unsolved problems in physics. Cosmic expansion also relates to the fundamental question of why the universe exists at all. Why is there something rather than nothing? The Big Bang represents the moment when space and time began, but this raises the question of what, if anything, existed before. Some theories suggest that quantum mechanics might allow the universe to emerge from literally nothing, with the total energy of the universe balancing to zero when you account for gravitational potential energy. But these ideas remain highly speculative. The anthropic principle offers one perspective on cosmic expansion. This principle notes that we observe the universe's properties partly because these properties allow our existence. If expansion proceeded much faster, structures like galaxies and stars couldn't form. If it proceeded much slower, the universe might have collapsed before life could emerge. We observe a universe with expansion rates compatible with our existence, because we couldn't exist in universes with very different expansion rates. This explains some cosmic coincidences through selection effects rather than fundamental physics. However, the anthropic principle has limitations. It explains why we observe certain properties, but doesn't explain why the universe has these properties in the first place. It's a philosophical perspective rather than a testable scientific theory. Many physicists prefer to seek deeper physical explanations for cosmic properties rather than invoking anthropic reasoning. The possibility of a multiverse, multiple universes with different properties, would make anthropic reasoning more powerful. If countless universes exist with different expansion rates, different amounts of dark energy, and different physical constants, then we necessarily find ourselves in one of the rare universes where conditions permit life. This would explain apparent fine-tuning without requiring a cosmic designer. However, multiverse theories are extremely difficult to test, since other universes would presumably be unobservable from ours. String theory, a candidate for unifying quantum mechanics with general relativity, naturally predicts extra spatial dimensions beyond the three we perceive. These theories often suggest that a vast number of possible universes could exist, each with different properties determined by how extra dimensions are configured. This string theory landscape might provide a framework for understanding our universe as one possibility among many. Some speculative ideas suggest that cosmic expansion might result from interactions with other universes or higher dimensional spaces. If our three-dimensional space is embedded in a higher dimensional realm, effects from that higher realm might appear as dark energy in our space. However, these ideas remain highly theoretical without clear observational predictions. Despite decades of research, fundamental questions about cosmic expansion remain unanswered. What is dark energy? Why does it have the density we observe, rather than being much larger or much smaller? Why did dark energy become dominant relatively recently in cosmic history, rather than earlier or later? Is the Hubble tension telling us about new physics or subtle measurement errors? Will expansion continue accelerating forever or change in the future? These questions drive current and future research. New telescopes and surveys will map the universe in unprecedented detail. The Vera Rubin Observatory will survey billions of galaxies, tracing cosmic structure evolution with statistical power far beyond current datasets. The Nancy Grace Roman Space Telescope will study dark energy using multiple complementary techniques. Ground-based gravitational wave detectors might detect signals from the early universe that could test inflation theories. Particle physics experiments search for dark matter particles and probe the quantum properties of space itself. If dark energy relates to quantum vacuum energy, then understanding it might require new discoveries in particle physics. The Large Hadron Collider and future accelerators might provide crucial insights. Theoretical work continues developing new models and testing their predictions against observations. Some theories modify general relativity on cosmic scales. Others propose new types of fields or particles. Computer simulations grow increasingly sophisticated, modeling cosmic evolution in detail and making precise predictions that observations can test. The expansion of space represents one of humanity's greatest discoveries about nature. Less than a century ago, we didn't know that other galaxies existed beyond our Milky Way. We thought the universe was static and eternal. Now we know that space itself grows, carrying billions of galaxies apart at accelerating rates driven by mysterious, dark energy that makes up most of reality. We understand the universe's age, its composition, and its large-scale structure. We can look back in time to when the cosmos was young and predict its distant future. Yet our understanding remains incomplete. The biggest mysteries in cosmology involve the very things that dominate the universe: dark matter and dark energy. These components shape cosmic expansion and determine the universe's fate, yet we know almost nothing about their fundamental nature. Solving these mysteries will require new physics beyond our current theories. Cosmic expansion also provides perspective on our place in the universe. We live in a gravitationally bound island in an expanding ocean. Our galaxy will remain intact, but most of the universe will drift beyond our observation. We exist during the universe's most interesting epoch, when stars shine and galaxies cluster together. This era represents a tiny fraction of cosmic time, a brief moment between the hot, dense past and the cold, empty future. The atoms composing your body were forged in stars that lived and died billions of years ago. Nuclear fusion in stellar cores built up elements heavier than hydrogen and helium, and supernova explosions scattered these elements through space. Subsequent generations of stars incorporated this enriched material, eventually forming planets where complex chemistry could occur. Cosmic expansion carried these atoms through space until they assembled into stars, planets, and eventually living beings capable of contemplating the cosmos itself. Your existence depends on cosmic expansion proceeding at exactly the right rate. If expansion were significantly faster, matter couldn't have clumped together to form galaxies and stars. Without stars, there would be no nuclear fusion to create heavy elements, no supernovae to scatter them, no planets, and no life. If expansion were significantly slower, the universe might have collapsed back on itself before stars completed their life cycles and produced the elements necessary for planets and biology. The expansion rate sits in a narrow range, permitting complex structures to develop. This apparent fine-tuning raises profound questions. Is it coincidence that the universe has properties permitting our existence? Some argue for design, suggesting the universe was intentionally configured to allow life. Others invoke the anthropic principle, noting we must observe a universe compatible with our existence because we couldn't exist otherwise. Still others propose multiverse scenarios where countless universes exist with different properties, and we naturally find ourselves in one permitting life. These questions blur the boundary between physics and philosophy, touching on issues of purpose and meaning. Cosmic expansion also connects to questions about determinism and predictability. Can we predict the universe's future with certainty, or do quantum effects introduce fundamental randomness? General relativity, which governs cosmic expansion on large scales, is deterministic. Given initial conditions, the equations predict future evolution uniquely, but quantum mechanics, which governs small scales, is probabilistic. Reconciling these frameworks remains an unsolved problem. The measurement of cosmic expansion illustrates how science progresses through increasingly precise observations. Early measurements were crude, with uncertainties of 50% or more. Hubble's original expansion rate estimate was wrong by a factor of 7 due to errors in distance measurements. Over decades, improved techniques reduced uncertainties to a few percent, then to 1%. Now we've reached the point where different methods disagree by amounts smaller than either method's uncertainty, revealing the Hubble tension. This tension exemplifies how science works. When two reliable methods give different answers, something interesting is happening. Either systematic errors affect one or both methods in ways we haven't identified, or our theoretical models are incomplete. Both possibilities drive scientific progress. Finding systematic errors requires understanding instruments and analysis methods in greater depth. Identifying missing physics requires creative thinking about what might be wrong with current theories. The Hubble tension might ultimately lead to the discovery of new particles, new fields, or modifications to general relativity. Or it might be resolved by identifying subtle measurement errors. Either outcome would represent progress. Science advances through this process of making precise measurements, comparing results, and resolving discrepancies. The expansion of space challenges our intuitions about reality in fundamental ways. We evolved to understand objects moving through static space, not space itself growing. Our brains developed models of reality based on everyday experience at human scales, where expansion effects are utterly negligible. Cosmic expansion operates at scales and rates beyond human perception, requiring abstract mathematical reasoning to comprehend. This disconnect between intuition and reality appears throughout modern physics. Quantum mechanics tells us that particles don't have definite positions until measured. Special relativity says that time passes at different rates for different observers. General relativity reveals that gravity is actually space-time curvature. These concepts violate common sense because common sense evolved to handle situations our ancestors encountered, not the extreme conditions where these effects become important. Understanding cosmic expansion requires accepting that mathematical models sometimes provide better guides to reality than intuition. The equations of general relativity predict expanding space, even though this seems impossible based on everyday experience. The observations confirm these predictions with extraordinary precision. We must trust the mathematics and observations, even when they conflict with intuition. The history of cosmic expansion research demonstrates the power of the scientific method. Observations drive theory development, theories make predictions, and further observations test those predictions. When observations conflict with theory, we modify the theory. When different observations conflict with each other, we investigate both until we understand the discrepancy. This iterative process has built a detailed understanding of how the universe evolves. Major breakthroughs in cosmology often came from unexpected observations. Hubble didn't set out to discover cosmic expansion. He was measuring galaxy distances and velocities. The cosmic microwave background was discovered accidentally by radio astronomers investigating interference in their antenna. Dark energy acceleration surprised researchers who expected expansion to be slowing down. These serendipitous discoveries remind us that nature often surprises us in ways we don't anticipate. The future of cosmic expansion research depends on building better instruments and developing better theories. Next-generation telescopes will observe fainter, more distant galaxies with higher precision. Improved gravitational wave detectors might observe signals from the early universe. Particle physics experiments might discover dark matter or reveal properties of dark energy. Theoretical work will develop new models and calculate their predictions with greater accuracy. Some questions might remain forever unanswered. If the universe is infinite and regions beyond our horizon have different properties, we cannot observe those regions to test theories about them. If dark energy results from quantum vacuum effects, we might lack the tools to calculate its properties from first principles. Physics has fundamental limits, and we might be approaching some of them. Nevertheless, the progress over the past century has been extraordinary. We've gone from thinking the universe is static to understanding its expansion history in detail. We've determined the universe's age, composition, and large-scale structure. We've observed the afterglow of the Big Bang and traced galaxy evolution across cosmic time. We've discovered dark energy and measured its effects. These achievements represent some of humanity's greatest intellectual accomplishments. The expansion of space also provides a cosmic perspective that can be both humbling and inspiring. We occupy a tiny planet orbiting an average star in a typical galaxy, one of hundreds of billions of galaxies in the observable universe. Cosmic expansion will eventually carry most of these galaxies beyond our observation. We exist during a brief cosmic moment when the universe is old enough for complex structures to develop, but young enough that stars still shine brightly. This perspective might seem to diminish human importance. In cosmic terms, we occupy an insignificant location during a brief moment in a vast universe dominated by dark matter and dark energy we don't understand. Yet this same perspective can be inspiring. We are the universe becoming aware of itself. Through us, the cosmos develops the capacity to observe its own expansion, to question its origins and fate, to create mathematical models describing its evolution. Consciousness might be rare in the universe, making it precious despite its cosmic insignificance. The expansion of space will continue long after humanity is gone. Even if we survive for millions or billions of years, we will eventually succumb to the same fate as all complex structures in an expanding universe. The stars will die, galaxies will scatter, and cosmic expansion will dilute all forms of energy until nothing interesting remains. Yet our existence, however brief, represents a genuine phenomenon that occurred in cosmic history. The fact that the universe produced beings capable of understanding cosmic expansion is itself remarkable. Some find the ultimate fate of the universe depressing. Heat death seems nihilistic, rendering all achievements meaningless on sufficiently long timescales. If everything ends in darkness and cold, what's the point? But this reaction might reflect a bias toward permanence that the universe doesn't share. Perhaps meaning doesn't require eternity. Perhaps the experience of consciousness, understanding, and creativity have value even if they don't last forever. Others find cosmic expansion inspiring rather than depressing. The universe is dynamic, evolving, and full of surprises. We live during an era of discovery, learning things about reality that previous generations couldn't have imagined. The questions we face today will drive research for decades or centuries to come. Future generations might look back on this era as the time when humanity first understood its place in an expanding cosmos. The mathematics describing cosmic expansion are both elegant and powerful. The Friedmann equations, derived from Einstein's general relativity, describe how the scale factor of the universe evolves based on its energy content. These relatively simple equations capture incredibly complex behavior, from decelerating expansion in the matter-dominated era to accelerating expansion in the dark energy-dominated era. The equations predict phenomena like the cosmic microwave background, the abundance of light elements, and the formation of large-scale structure, all of which observations confirm. The Robertson-Walker metric describes the geometry of an expanding universe that looks the same in all directions. This metric allows cosmologists to calculate how light travels through expanding space, how distances change over time, and how the expansion rate affects cosmic evolution. The mathematical framework provides precise predictions that observations can test. The agreement between mathematical predictions and observational data validates our understanding of cosmic expansion. Redshift provides a direct observable connecting theory to observation. The amount by which light is redshifted reveals how much the universe has expanded during the light's journey. This allows astronomers to look backward through cosmic history, observing galaxies as they appeared billions of years ago. By measuring redshifts for large samples of galaxies and comparing them to other distance indicators, astronomers map cosmic expansion history in detail. The concept of co-moving coordinates provides an elegant way to describe positions in expanding space. In co-moving coordinates, galaxies that move only with expansion remain at fixed coordinates, even though the physical distances between them increase. This mathematical framework separates the effects of expansion from genuine motion through space. Galaxies might have small velocities relative to the expansion flow, called peculiar velocities, but these are typically much smaller than the recession velocities due to expansion itself. The critical density concept emerges naturally from the Friedmann equations. This represents the density needed for the universe to be geometrically flat. Higher density creates positive curvature like a sphere, while lower density creates negative curvature like a saddle. Observations show our universe has density very close to critical, meaning space is nearly flat on large scales. This flatness is another puzzle that cosmic inflation explains by stretching any initial curvature to unmeasurable levels. The deceleration parameter quantifies whether expansion is speeding up or slowing down. Before dark energy was discovered, cosmologists expected this parameter to be positive, indicating deceleration due to gravity. The discovery that it's actually negative, indicating acceleration, revolutionized cosmology, and led to the dark energy concept. Current measurements show the deceleration parameter has been negative for about 5 billion years, after being positive for the first 8 billion years or so. The equation of state for dark energy relates its pressure to its energy density. Different values correspond to different physical interpretations. A cosmological constant has an equation of state of -1, meaning its density remains constant as the universe expands. Other values would indicate evolving dark energy that changes over time. Precise measurements of the equation of state could distinguish between these possibilities, helping reveal dark energy's nature. The sound horizon at recombination, the distant sound waves could travel in the early universe before it became transparent, creates a characteristic scale in the cosmic microwave background pattern. This scale serves as a standard ruler that cosmologists use to measure cosmic distances and expansion rates. The precise measurement of this scale in the cosmic microwave background contributes to the Hubble tension, as it predicts a different expansion rate than local measurements find. Baryon acoustic oscillations represent another standard ruler for measuring cosmic distances. These are subtle patterns in galaxy clustering created by sound waves in the early universe, similar to those producing the cosmic microwave background pattern, but imprinted on matter distribution. By measuring these patterns in galaxy surveys, astronomers can determine expansion rates at different cosmic times, tracing how expansion has evolved. The cosmic distance ladder represents the series of techniques astronomers use to measure distances at progressively larger scales. Nearby stars can be measured using parallax, the apparent shift in position as Earth orbits the Sun. Cepheid variables extend the distance scale to nearby galaxies. Type Ia supernovae extend it further to distant galaxies. Each step depends on the previous one, so errors can accumulate. Much of the Hubble tension centers on whether systematic errors affect these distance measurements. The age of the universe follows directly from the expansion history. By integrating the Friedmann equations backward in time, cosmologists calculate when the scale factor was 0, marking the Big Bang. Different values of the Hubble constant give different ages. The cosmic microwave background analysis suggests an age of about 13.8 billion years. If the local expansion rate measurement is correct, the universe would be slightly younger, about 13.0 billion years. This difference might create problems for models of structure formation and stellar evolution. The look-back time to any redshift can be calculated using the expansion history. This tells us how long ago light was emitted based on its redshift. The most distant galaxies observed by Webb have look-back times exceeding 13 billion years, meaning we see them as they were when the universe was less than 1 billion years old. These galaxies appear surprisingly mature for their age, suggesting structure formation began earlier or proceeded more efficiently than models predicted. The comoving distance to any redshift accounts for expansion during the light's travel time. This represents the distance the galaxy would be at today if we could freeze expansion and measure the distance. The comoving distance to the cosmic microwave background is about 46 billion light-years, much larger than the 13.4 billion light-years the light has travelled, because expansion carried the source farther away while the light was in transit. The angular diameter distance affects how large objects appear at different redshifts. Counterintuitively, very distant objects can appear larger than somewhat less distant objects due to expansion effects. Light from extremely distant objects was emitted when the universe was smaller and the object was closer, making it appear larger than expected. This creates a minimum apparent size for distant objects at a redshift of about 1.5. The luminosity distance affects how bright objects appear at different redshifts. This distance is always larger than the angular diameter distance due to expansion effects. Light gets redshifted during its journey, reducing its energy. The expansion also dilutes photon density as space grows. Both effects make distant objects appear dimmer than they would in a static universe, and both effects increase with redshift. These different distance definitions might seem confusing, but they reflect the reality that expansion affects measurements in complex ways. In a static universe, all distance definitions would agree. In an expanding universe, we must carefully specify which distance concept we're using. Each definition is useful for different purposes. Angular diameter distance matters for measuring object sizes. Luminosity distance matters for measuring brightness, and co-moving distance matters for theoretical calculations. The horizon problem that inflation solves can be quantified precisely. In a universe that's been expanding at constant or decreasing rates since the Big Bang, causally connected regions can only be separated by about twice the age of the universe times the speed of light. Yet the cosmic microwave background shows uniformity across regions separated by much larger distances. These regions couldn't have communicated without inflation stretching causally connected patches to cosmic scales. The flatness problem that inflation solves is similarly quantifiable. Any deviation from critical density grows over time in a standard Big Bang model. For the universe to be as close to flat as we observe today, it would have had to be extraordinarily flat in the early universe, differing from critical density by less than 1 part in 10 to the power of the 62nd power at 1 second after the Big Bang. This extreme fine-tuning seems implausible without inflation, which naturally drives the density to critical values. The monopole problem provided another motivation for inflation. Grand unified theories of particle physics predict that topological defects called magnetic monopoles should have been produced in the early universe. These would be extremely massive and should be common. Yet we've never observed one. Inflation solves this by diluting monopoles to undetectable density through exponential expansion. Inflation makes specific predictions about the properties of cosmic microwave background fluctuations. These fluctuations should be nearly scale invariant, meaning they have similar amplitudes at different scales. They should be Gaussian, meaning their statistical properties follow a normal distribution. They should be adiabatic, meaning density fluctuations and temperature fluctuations are correlated in specific ways. Observations confirm all these predictions, providing strong support for inflation despite its speculative nature. The inflationary epoch itself remains mysterious. We don't know what field drove inflation, what its properties were, or exactly when inflation occurred. Different inflation models make slightly different predictions for observable quantities, like the amplitude and scale dependence of fluctuations. Future observations might distinguish between models, revealing more about inflation's nature. Eternal inflation represents an extension of standard inflation models. In many models, inflation doesn't end everywhere simultaneously. Different regions stop inflating at different times, and some regions might continue inflating forever. This creates a vast multiverse of post-inflationary bubble universes, each potentially with different properties. Our observable universe would be just one bubble in an infinite inflating space. This multiverse scenario has profound philosophical implications. If infinite universes exist with different properties, then the anthropic principle becomes more powerful. We observe a universe with properties permitting our existence simply because we couldn't exist in universes with very different properties. This explains apparent fine-tuning without invoking design or fundamental principles. However, it also makes some questions about our universe's properties fundamentally unanswerable, since they'd just be random outcomes in the space of all possibilities. The measure problem in eternal inflation asks how to calculate probabilities when infinite outcomes occur. If inflation produces infinitely many universes with various properties, What does it mean to say one outcome is more probable than another? Standard probability theory doesn't apply to infinite sets in straightforward ways. This measure problem remains unsolved, making it difficult to extract definite predictions from eternal inflation models. String theory landscape scenarios suggest that the number of possible post-inflationary universes might be enormous, perhaps 10 to the 500th power or more. Each possibility corresponds to different ways of configuring extra dimensions and different values of physical constants. This vast landscape of possibilities makes anthropic reasoning more plausible, but also reduces the theory's predictive power, since almost any observation could be accommodated somewhere in the landscape. Critics argue that multiverse theories aren't science because they're not falsifiable. If we can't observe other universes, we can't test theories about them. Proponents counter that multiverse predictions might be testable indirectly through their effects on our universe, or through statistical arguments about what types of universes should be common. This debate touches fundamental questions about what makes a theory scientific. The cosmological constant problem represents one of the deepest puzzles in physics. Quantum field theory predicts that empty space should have enormous energy density from virtual particle fluctuations. Yet observations show that dark energy density is tiny compared to this prediction. The discrepancy is a factor of 10 to the 120th power, the largest disagreement between theory and observation in science. Understanding this requires either new physics that cancels the vacuum energy or fundamentally rethinking quantum field theory. The coincidence problem asks why dark energy and matter have comparable densities today. Matter density decreases as the universe expands while dark energy density stays constant. These cross over at a specific time, and we happen to live near that crossover. This seems like an incredible coincidence unless there's some physical mechanism linking dark energy to matter density, or unless anthropic reasoning explains it. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy. These theories change Einstein's equations on large scales while preserving their well-tested predictions on smaller scales. Examples include F of R gravity, which modifies the form of the gravitational action, and theories with extra scalar fields coupled to gravity. Some of these theories can mimic dark energy effects while avoiding the cosmological constant problem. However, most face difficulties matching all cosmological observations or predicting new effects that aren't observed. The tests of general relativity on cosmic scales provide crucial constraints on modified gravity theories. Gravitational lensing, the bending of light by gravity, must work as Einstein predicted. The growth rate of cosmic structure must match predictions. Gravitational wave propagation must agree with observations. These tests eliminate many proposed alternatives to dark energy, though some survive current constraints. Dark energy surveys use multiple complementary techniques to constrain dark energy properties. They measure galaxy clustering to trace structure growth. They observe supernovae to map expansion history. They measure weak gravitational lensing to probe matter distribution. They study galaxy clusters to understand how structure forms. Combining these techniques reduces systematic errors and provides robust constraints on dark energy behavior. The Vera Rubin Observatory, scheduled to begin operations soon, will conduct the legacy survey of space and time, observing billions of galaxies and detecting millions of supernovae. This survey will measure dark energy properties with unprecedented precision, potentially revealing whether dark energy evolves over time. The sheer statistical power of observing billions of objects will reduce measurement uncertainties dramatically. The Nancy Grace Roman Space Telescope will study dark energy using gravitational lensing and supernova observations from space. Space-based observations avoid atmospheric distortions that limit ground-based telescopes, providing cleaner data. Roman will observe infrared wavelengths, allowing it to study distant galaxies and trace structure evolution across cosmic time. Gravitational wave astronomy offers a completely independent way to probe cosmic expansion. Colliding black holes and neutron stars produce gravitational waves that travel through space at light speed. These waves also get redshifted by cosmic expansion. By detecting gravitational waves and identifying the host galaxies where the collisions occurred, astronomers can measure expansion rates without relying on the traditional distance ladder. This could help resolve the Hubble tension by providing a completely independent measurement method. The Laser Interferometer Space Antenna, or LISA, scheduled to launch in the 2030s, will detect gravitational waves from massive black hole mergers across cosmic distances. These observations will probe expansion rates in different cosmic epochs, tracing dark energy's influence over billions of years. LISA might detect signals from the early universe that could test inflation theories or reveal new physics. The expansion of space affects our ability to detect gravitational waves. Low-frequency gravitational waves have wavelengths comparable to distances between detectors. As space expands, it stretches these waves, shifting their frequencies. Future detectors must account for cosmological effects when analyzing signals from distant sources. Cosmic expansion also affects neutrino astronomy. Neutrinos are ghostly particles that barely interact with matter, allowing them to escape from extremely dense regions like supernovae cores and travel across the universe largely unimpeded. The cosmic neutrino background, analogous to the cosmic microwave background but consisting of neutrinos instead of photons, was produced when the universe was about 1 second old. This background has been redshifted by expansion to incredibly low energies, making it extremely difficult to detect with current technology. Future neutrino detectors might observe high-energy neutrinos from distant astrophysical sources, providing another window on cosmic expansion. Neutrino oscillations, the quantum mechanical phenomenon where neutrinos change type as they travel, are affected by cosmic expansion in subtle ways. Precision measurements of neutrinos from distant sources could provide information about expansion history. The expansion of space connects to information theory in interesting ways. As the universe expands and cools, the maximum amount of information that can be stored in a given volume changes. The holographic principle in physics suggests that the maximum information content of a region is proportional to its surface area rather than its volume. As the universe expands, the total information capacity grows. This has implications for questions about whether the universe can function as a computer and whether there are limits to what can be computed or known. Black hole thermodynamics relates entropy, information, and gravity in ways that might illuminate dark energy's nature. Black holes have entropy proportional to their surface area, and they radiate energy according to their temperature. The relationship between gravitational physics and thermodynamics might extend to cosmology, with dark energy related to cosmic entropy or information content. These ideas remain speculative but suggest deep connections between seemingly unrelated phenomena. The simulation hypothesis proposes that our reality might be a computer simulation run by an advanced civilization. If true, cosmic expansion might be a feature of how the simulation is programmed rather than fundamental physics. This idea is untestable with current methods and raises philosophical questions about the nature of reality. Most physicists consider it an interesting thought experiment rather than a scientific hypothesis. Quantum gravity theories attempt to reconcile quantum mechanics with general relativity. These theories might provide insights into cosmic expansion's ultimate origin. Loop quantum gravity suggests that space has discrete structure at tiny scales. String theory posits that particles are actually vibrating strings in higher dimensional space. Both approaches might shed light on how space itself can expand and what happened at the Big Bang when quantum effects were crucial. The Planck scale represents the frontier where quantum gravity effects become important. At energies approaching the Planck energy, or distances approaching the Planck length, our current theories break down. The Big Bang singularity exists at this frontier, where we cannot apply classical general relativity. Understanding what happened at the very beginning requires a theory of quantum gravity that we don't yet possess. Some quantum gravity theories suggest the Big Bang wasn't actually a singularity, but rather a transition from a previous state. Loop quantum cosmology models propose that the universe might have undergone a big bounce, contracting to a minimum size before expanding again. In these scenarios, cosmic expansion represents the rebound phase following maximum contraction. However, these ideas remain highly speculative without clear observational tests. The arrow of time connects to cosmic expansion in subtle ways. Time appears to flow in one direction, from past to future. This directionality relates to increasing entropy, the second law of thermodynamics. Cosmic expansion contributes to increasing entropy by spreading energy across ever larger volumes. The expansion of space might be related to why time has a direction rather than being reversible like most fundamental physics equations. Quantum entanglement, where particles maintain mysterious correlations across arbitrary distances, raises questions about cosmic expansion. When space expands between entangled particles, does this affect their correlation? Current theory says no, entanglement persists regardless of distance. But understanding how quantum correlations extend across expanding space remains an active research area with potential implications for quantum gravity theories. The fine structure constant, which characterizes electromagnetic interaction strength, might vary across cosmic time or space. Some observations have hinted at tiny variations, though results remain controversial. If fundamental constants evolve as the universe expands, this would require new physics beyond current theories. Searches for varying constants use quasar spectra from different cosmic epochs to look for tiny shifts in atomic spectral lines. Cosmic expansion affects how we think about causality and determinism. Events at different locations in an expanding universe can be causally disconnected if space between them grows faster than light can travel. This creates event horizons similar to those around black holes. Information cannot pass between causally disconnected regions, limiting what can be known or predicted about distant parts of the universe. The cosmic censorship hypothesis in general relativity suggests that singularities like the Big Bang and those inside black holes are always hidden behind event horizons. We cannot observe singularities directly because expansion or black hole horizons prevent information from reaching us. This protects the predictability of physics by ensuring singularities don't affect observable regions. Whether cosmic censorship holds in all situations remains an open question. Cosmic expansion influences how we search for extraterrestrial intelligence. If technological civilizations commonly develop on planets around other stars, expansion limits which civilizations could communicate with us. Signals from sufficiently distant civilizations would be redshifted to undetectable frequencies. Civilizations in galaxies beyond our local group will eventually move beyond our cosmic horizon, making communication impossible even in principle. The Fermi paradox asks why we haven't detected signs of alien civilizations despite the vast number of stars and planets. One possible resolution involves cosmic expansion timescales. If intelligent civilizations are rare or short-lived, the expanding universe might prevent them from ever making contact. The window for communication between civilizations might be smaller than the timescales for expansion to carry them out of contact. Cosmic expansion also affects proposals for interstellar travel. Any civilization attempting to colonize the galaxy must contend with the fact that distant galaxies recede at relativistic speeds. Traveling to another galaxy cluster would require not just achieving speeds close to light speed, but also overcoming the ongoing expansion carrying the destination farther away. This makes intergalactic colonization extraordinarily challenging, potentially confining intelligent life to individual galaxy clusters. The observable universe contains approximately 2 trillion galaxies based on current estimates. Each galaxy contains hundreds of billions of stars on average. This gives something like 10 to the 24th power stars in the observable universe, far more than grains of sand on all Earth's beaches. The number of planets likely exceeds the number of stars, providing countless potential locations for life to develop. Yet despite these enormous numbers, the observable universe represents an infinitesimally small fraction of the total universe if space is truly infinite. Infinity is incomprehensibly large. Any finite number, no matter how enormous, is zero compared to infinity. If the universe is infinite, then our observable region, containing trillions of galaxies, is effectively nothing compared to the totality of reality. This perspective both humbles and inspires. We occupy an insignificant corner of an infinite cosmos, yet we're the part of the universe that has developed understanding. Through science, we've deciphered how cosmic expansion works, how structure forms, and how the universe evolves. We've looked back to when the universe was young and forward to its ultimate fate. This understanding represents a genuine achievement regardless of our cosmic insignificance. The expansion of space demonstrates that the universe is fundamentally dynamic rather than static. Change represents the cosmic norm. The universe had a beginning, evolves through various epochs, and faces an ultimate fate determined by dark energy's behavior. This dynamism contrasts with ancient philosophical ideas about eternal, unchanging reality. Modern cosmology reveals a universe of constant change and evolution. This dynamism extends to everything within the universe. Stars are born, live, and die. Galaxies form, merge, and evolve. Even seemingly permanent structures like atoms undergo radioactive decay over sufficient timescales. Everything changes, and cosmic expansion provides the backdrop against which these changes occur. The concept of eternal return, proposed by some philosophers, suggests that an infinite universe with infinite time must eventually repeat all configurations. If the universe is infinite and expansion continues forever, then somewhere in the infinite future, the same configuration of particles that makes up your consciousness must recur. This leads to strange philosophical implications about identity and existence. However, the accelerating expansion driven by dark energy might prevent such recurrences by diluting matter to zero density. Cosmic expansion has profound implications for the meaning and purpose questions that philosophy and religion address. If the universe had a beginning, does this imply a cause or creator? If expansion continues forever toward heat death, does this render existence meaningless? Different philosophical and religious traditions answer these questions differently, and science alone cannot resolve them. Science describes how the universe behaves, not why it exists or what meaning to assign it. Some religious traditions have embraced Big Bang cosmology as compatible with creation narratives. The idea of a cosmic beginning aligns with creation ex nihilo, creation from nothing. However, others note that the Big Bang represents the beginning of this phase of cosmic evolution, not necessarily absolute beginning. The quantum gravity era before the Big Bang might connect to a previous state, making the question of ultimate origin more complex. Eastern philosophical traditions that emphasize cyclical time find resonance in cyclic universe models, where Big Bangs follow big crunches in endless succession. However, current observations favoring eternal expansion fit less well with these traditions. The dialogue between cosmology and philosophy remains active, with each informing the other's questions and perspectives. The expansion of space ultimately reminds us that we participate in something vastly larger than ourselves. Every atom in your body has a cosmic history stretching back to the Big Bang. The forces that bind those atoms were established in the universe's first moments. The elements were forged in stellar furnaces and scattered by supernovae. The Earth formed from this enriched material, and life emerged through chemical evolution. Your consciousness represents the universe's capacity for self-awareness. When you look up at the night sky, you're observing cosmic history. The light reaching your eyes was emitted years, centuries, or millennia ago. The most distant objects visible to telescopes appear as they were billions of years ago, when the universe was young. Astronomy is time travel, allowing us to observe the past directly. Cosmic expansion makes this possible by giving the universe a history, an evolution from hot, dense beginnings to the structured cosmos we inhabit. The questions raised by cosmic expansion continue driving scientific research. What is dark energy? Will expansion continue forever? Is the Hubble tension revealing new physics? What happened before the Big Bang? Does the universe have a beginning, or is it part of an eternal cycle? Can we test inflation theory directly? These questions motivate observations, experiments, and theoretical work. Future discoveries might revolutionize our understanding as profoundly as past breakthroughs did. The discovery of cosmic expansion itself, of the cosmic microwave background, of dark energy acceleration, all transformed cosmology. The next transformative discovery might come from resolving the Hubble tension, from detecting primordial gravitational waves, from discovering dark matter particles, or from observations we haven't yet imagined. The history of science shows that nature often surprises us. Our theories capture important truth about reality, but they're always incomplete. The standard model of cosmology successfully explains countless observations, yet we know it's incomplete because it cannot account for dark matter and dark energy's fundamental nature. Future theories will explain these phenomena, likely revealing new surprises in the process. The expansion of space connects the largest cosmic scales to the smallest quantum scales. Inflation theory links quantum fluctuations to galaxy formation. Dark energy might arise from quantum vacuum effects. The Big Bang represents a moment when quantum gravity effects were crucial. Understanding cosmic expansion fully requires understanding how quantum mechanics and general relativity fit together, one of physics' greatest unsolved problems. The very concept of space expanding challenges us to think carefully about what space is. Pre-Einstein physics treated space as an absolute, unchanging background. Einstein's relativity revealed that space and time are dynamic, affected by matter and energy. Quantum theories suggest space might have discrete structure at tiny scales. Understanding space's fundamental nature remains an active area of research bridging cosmology, relativity, and quantum physics. The endpoint of our cosmic journey returns us to the beginning. We live in an expanding universe that began 13.8 billion years ago in an incredibly hot, dense state. Space itself has grown by enormous factors since then, carrying galaxies apart at accelerating rates. This expansion will continue far into the future, eventually leaving gravitationally bound islands isolated in an exponentially growing cosmos. The expansion has no center and no edge. It affects all of space uniformly, creating a situation where every observer sees identical expansion patterns from their location. Dark energy drives the current acceleration, though we don't understand its fundamental nature. Dark matter provides the gravitational scaffolding for structure formation, though we don't know what particles comprise it. Together, dark matter and dark energy account for 95% of cosmic reality, with ordinary matter making up the remaining 5%. We are made of the minority constituent in a universe dominated by mysterious components. The Hubble tension reveals that our understanding remains incomplete. Different measurement methods give different expansion rates, suggesting either systematic errors or missing physics. Resolving this tension might lead to important discoveries about how the universe works. Cosmic expansion connects us to the deepest questions about existence. Why is there something rather than nothing? Why does the universe have the properties it does? What is the ultimate fate of reality? Science provides frameworks for addressing these questions, but complete answers might remain forever elusive. The universe might be infinite, with most of reality forever beyond our observation. We can understand only what lies within our cosmic horizon. Yet the scope of that understanding is remarkable. From observations of distant galaxies, we've reconstructed cosmic history across 13.8 billion years. We've traced the evolution from a hot, dense state to the structured universe we inhabit. We've discovered that expansion accelerates, driven by mysterious dark energy. We've mapped the cosmic microwave background and decoded its message about the early universe. We've determined the universe's age, composition, and geometry. These achievements represent humanity at its best, using reason and observation to understand reality. The process of scientific discovery continues. Each answer raises new questions. Each observation refines our understanding while revealing new puzzles. The Hubble tension exemplifies this. As measurements became more precise, they revealed a discrepancy that demands explanation. This tension drives current research and will likely lead to important insights, whether through discovering systematic errors or revealing new physics. The expansion of space teaches profound lessons about the nature of knowledge itself. Some questions might be unanswerable, not because we lack clever enough theories, but because physics itself limits what can be known. Regions beyond our cosmic horizon are fundamentally unobservable. The quantum gravity era at the Big Bang might be inaccessible to direct observation. We must accept that complete knowledge of the universe might be impossible, yet this doesn't diminish the value of what we can learn. Science progresses through a combination of theoretical insight and observational testing. Einstein developed general relativity through pure thought, using mathematical beauty and logical consistency as guides. His equations predicted phenomena like gravitational waves and black holes decades before observations confirmed them. Yet theory alone is insufficient. Observations of cosmic expansion, the cosmic microwave background, and dark energy acceleration were essential for building modern cosmology. The interplay between theory and observation drives progress. The community aspect of science also matters crucially. Individual scientists make contributions, but understanding emerges from thousands of researchers checking each other's work, replicating observations, and testing theoretical predictions. The Hubble tension persists precisely because multiple independent teams have confirmed both measurements. This collective scrutiny makes scientific knowledge reliable despite human fallibility. The expansion of space will continue long after humanity's time has passed. Even if we survive for millions of years, we represent a brief moment in cosmic history. The universe existed for billions of years before life appeared on Earth. It will continue for unimaginably longer after the last star dies. Yet our existence, however brief, represents a genuine phenomenon that occurred. The universe produced beings capable of understanding cosmic expansion. This fact has value independent of its duration. Consciousness might be extremely rare in the universe. Despite billions of stars and planets, we've found no evidence of other intelligent life. This might mean consciousness is precious, making human understanding of cosmic expansion a remarkable achievement. Or it might mean life is common, but technological civilizations are short-lived, a sobering thought given our own challenges. Either way, our capacity to understand the cosmos deserves recognition. The relationship between observer and cosmos raises philosophical questions. Does the universe need observers to exist? Quantum mechanics suggests observation plays a role in determining physical states, though the extent and nature of this role remain debated. Cosmology suggests the universe existed for billions of years before any observers evolved. Reconciling these perspectives remains philosophically challenging. The anthropic principle notes that observers can only exist in universes compatible with their existence. This creates selection effects in what we observe. We find ourselves in a universe where expansion permits structure formation because we couldn't exist otherwise. This explains some apparent cosmic coincidences without invoking design or fundamental principles. However, it doesn't explain why any universe exists or why physical laws have the form they do. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that all possible outcomes of quantum measurements occur in different branches of reality. This creates an even vaster multiverse than eternal inflation alone, with every quantum event spawning new universes. In this scenario, cosmic expansion occurs differently in different branches, and we observe one particular history. These ideas remain highly speculative and philosophically controversial. The information content of the universe relates to cosmic expansion in ways we're still exploring. The holographic principle suggests that all information in a three-dimensional region can be encoded on its two-dimensional boundary. This counterintuitive idea emerges from black hole thermodynamics and might apply to the universe as a whole. As the universe expands, its boundary grows, increasing its information capacity. What this means for physics and consciousness remains unclear. Cosmic expansion connects to the question of whether mathematics is discovered or invented. The mathematical structures describing expansion exist independently of human minds. We discovered these structures through studying nature, but the mathematics itself seems to have an existence beyond human thought. This suggests a Platonic view where mathematical truth is absolute and eternal, existing outside physical reality. Yet we can only access mathematics through human minds, raising questions about its ultimate nature. The predictive power of mathematics in describing cosmic expansion is remarkable. Einstein's equations, derived from abstract mathematical principles, accurately predicted phenomena never observed until decades later. The Friedmann equations describe cosmic expansion with precision, even though they emerged from pure mathematical manipulation of Einstein's theory. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, remains philosophically puzzling. The expansion of space has inspired art, literature, and philosophy beyond its scientific significance. The idea of an expanding universe appears in science fiction, poetry, and visual art. The cosmic perspective influences how people think about their place in reality. For some, expansion inspires wonder and awe. For others, it provokes existential anxiety about meaninglessness and insignificance. These varied responses show how scientific discoveries resonate through culture. Educational efforts to communicate cosmic expansion face challenges. The concept violates everyday intuition, requiring abstract thinking about expanding space rather than objects moving through space. Visual analogies like balloon surfaces help but have limitations. Effective science communication must balance accuracy with accessibility, conveying core concepts without oversimplifying to the point of error. The history of cosmology shows how scientific consensus can shift dramatically when new evidence emerges. Before Hubble, most astronomers accepted a static universe. The discovery of expansion forced a complete reconceptualization. The discovery of dark energy acceleration similarly upended expectations. Scientists must remain open to evidence that challenges prevailing theories, even when those theories have been successful. Confirmation bias, the tendency to favor evidence supporting existing beliefs, poses challenges for cosmology research. Researchers might unconsciously interpret ambiguous data in ways supporting their preferred theories. Peer review and replication help mitigate this, but it remains a concern. The Hubble tension persists partly because researchers have rigorously tested both measurements, resisting confirmation bias that might dismiss one result. The sociology of science influences how cosmology develops. Scientific communities have power structures, funding priorities, and fashions in research topics. These social factors can accelerate or impede scientific progress. The dark energy field exploded after 1998 because the discovery was recognized as important and funding flowed to dark energy research. Other areas might languish due to lack of recognition or resources. The public understanding of cosmic expansion varies widely. Some people grasp the basic concept that space grows, while others hold misconceptions about galaxies flying through static space. Science education tries to correct these misconceptions, but they persist partly because the truth is so counterintuitive. Improving public scientific literacy remains an ongoing challenge. The expansion of space intersects with questions about the origin of physical law. Why does gravity follow Einstein's equations rather than some other mathematical form? Why do quantum fields behave as they do? Some theories propose that physical laws emerge from more fundamental principles, perhaps related to symmetries or optimization principles. Others suggest laws are arbitrary, selected by chance in our particular universe from among many possibilities. The landscape of possible physical theories is vast. Different mathematical structures could describe possible universes with different laws. Understanding why our universe has its particular laws might require understanding this broader landscape. String theory's landscape of possibilities represents one attempt at this understanding, though it remains controversial and incomplete. The expansion of space demonstrates that the most fundamental aspects of reality are dynamic and evolving. Space itself changes. Time progresses. Physical states evolve according to dynamical laws. This dynamism contrasts with Platonic ideals of eternal, unchanging forms. Modern physics reveals a universe of flux and change at all levels, from quantum fields to cosmic expansion. The rates of cosmic expansion in different eras show how the universe's dynamics have changed. During inflation, expansion proceeded exponentially. During the radiation-dominated era, it slowed rapidly. During matter domination, it decelerated more gradually. Now, in the dark energy era, it accelerates. The universe has transitioned through distinct epochs, each with different physical conditions and expansion rates. The transition between epochs occurred at specific times when different energy components became dominant. The radiation to matter transition occurred about 50,000 years after the Big Bang, when the universe cooled enough that matter energy density exceeded radiation energy density. The matter to dark energy transition occurred about 5 billion years ago, when cosmic expansion had diluted matter enough that dark energy became dominant. These transitions mark major changes in cosmic evolution. Future transitions might occur if dark energy evolves. If dark energy strengthens, it might eventually unbind all structures in a big rip. If it weakens, expansion might slow or reverse. If it oscillates, the universe might enter a new phase of evolution we haven't imagined. The DESI observations hinting at evolving dark energy, if confirmed, would indicate we're approaching or entering such a transition. The cosmic calendar, which compresses the universe's history into 1 year for perspective, illustrates the brevity of human existence. If the Big Bang occurred on January 1st, the solar system formed in early September, complex life emerged in mid-November, and all of human history occupies the last few seconds before midnight on December 31st. This perspective shows how recent humanity is compared to cosmic timescales. Extending this calendar forward shows cosmic expansion's long-term effects. The last stars will die a few years into the future at this scale. Black hole evaporation would occur after times requiring many pages to write out. Heat death lies in the incomprehensibly distant future. The universe's interesting epoch, when stars shine and complex structures exist, represents a brief moment between empty beginnings and empty endings. Yet this brief moment includes phenomena of extraordinary richness. Stars create heavy elements through nuclear fusion. Planets form from interstellar dust. Chemistry on those planets becomes complex enough for life to emerge. Biological evolution produces intelligent species capable of observing and understanding the cosmos. All this complexity emerges during the universe's structurally interesting phase, enabled by expansion rates that permit structure formation. The expansion of space creates the conditions for this complexity by setting timescales. Too rapid expansion would prevent structure formation. Too slow expansion would lead to recollapse before complexity develops. The observed expansion rate lies in the range permitting billions of years of stable cosmic evolution, during which stars can form multiple generations and life can evolve. This timing seems fortunate, though anthropic reasoning suggests we shouldn't find it surprising. The future of cosmic expansion remains uncertain, with multiple scenarios still possible. Current observations favor constant dark energy leading to heat death, though other outcomes can't be ruled out. People respond differently to contemplating cosmic expansion, some finding it liberating, others disturbing, still others motivating. Understanding expansion requires integrating gravity, quantum mechanics, thermodynamics, and nuclear physics into a coherent picture. Modern cosmology has become deeply interdisciplinary, combining physics, astronomy, mathematics, and data science to analyze billions of galaxies. The field offers diverse career paths in universities, laboratories, space agencies, and increasingly private industry. Public fascination with cosmology creates opportunities for science communication, though explaining concepts that violate everyday intuition presents challenges. International collaborations drive major projects forward, with open data policies accelerating discovery. Technologies developed for cosmology research, from GPS corrections to CCD sensors, find applications far beyond astronomy. The expansion of space creates subtle complexities in how we measure distances and interpret observations of distant objects. The cosmic web structure reveals how gravity and expansion competed to shape the universe's architecture. Observations of the cosmic microwave background, galaxy distributions, and other phenomena provide crucial tests that cosmological models must pass. Future experiments will narrow uncertainties about dark energy's nature and might detect primordial gravitational waves from inflation. We exist during a remarkable transition epoch when both matter and dark energy significantly shape cosmic dynamics. The expansion continues carrying galaxies apart, writing a story across billions of years that conscious beings briefly emerge to comprehend before the universe moves on toward its ultimate fate.